Hello guys, in this video, this is the first video where we finally are going to have a look at a much more complex behavior. Try to basically put everything together, everything we have seen so far together to achieve something a little bit more complex and a little bit more modular. So for the first time, I'm going to start calling the assets that I create, just to specify a little bit of naming convention. Rather than solvers, I'm going to start creating the final result, which is what we're looking here. I'm going to refer to as a module. A module being a combination of rig logic that is mostly achieved via a combination of solvers. Now, in the previous video, we saw how to achieve different kind of solvers, and then we saw how we can create a little bit more intelligent logic through the creation of functions. So in this video, there is a lot of stuff going on. The goal I set for myself for this video is to have a higher level in the rig graph, to have a very high level language, if you want, that makes the graph really simple to read. So there is a lot of stuff in here, but I'm gonna try to explain it from macro to micro, and see how the encapsulation works. So the first thing, let's see at the final result. What I wanted to achieve basically, it's IK-FK solver. So this is an arm. We have an FK arm. Nothing fancy here. I want to be able to pose the arm, and I want to be able to perform a switch in place and switch with a different behavior such as IK. Okay, the pull vector is over there. Let me grab it. Here we go. And then potentially move back to FK with no changes whatsoever in the shape of the geometry. Okay, so we saw this kind of behavior in the past. We put together certain behaviors where we were able to switch kinematics without having any change in shape. So the animator can key the switch and change the way he can animate things, using either IK, FK, spine, reverse spine, whatever you can think of. But the way now I implemented the module is by leveraging a lot the idea of encapsulation. And by that I mean generating functions that are trying to solve a very specific problem, and then by combining those functions together, I was able to get a graph that is much simpler. A high-level graph, the rig graph. Before we jump in, I also want to say a couple of things, couple of observation, let's say. By moving to Unreal 5 and leveraging off finally the function mechanism that was not available in the previous control rig, the first thing I want you to notice is that my number of variables is extremely low now compared to the previous solvers. And this is because most of the logic is expressed or achieved by input inside a function. Okay, so you can see that here I'm only specifying 3 different variables, which are basically linear color, and this is for customizing the color of the rig to make the ARM module a little bit more customizable. We can see what this does later. Let's have a look at the graph. We have a setup event in a sequence, and the first node that appears is something that is a function, and this is basically this whatever it takes care of performing the solver IK-FK placement position. You can specify the variables here, so not here anymore. You can specify the variables as input of the function, and by having these exposed, this makes this graph adaptable to a different kind of bone configuration or bone naming. Okay, so this is the first thing. The second thing I want you, and then after that, I simply do the same thing, but for the hand. So I'm keeping separate the idea of having an IK-FK solver to a solver that solves the hand. And the same concept is applied here. We have different variables to input. So from here, this is the setup event. That is the event that takes care of placing the joints and initializing values. In the forward solve, it's very, very similar. The only additional thing, and we're going to see how this is achieved, is that I'm taking care of making the controls visible or invisible depending on which kinematics I'm on, and I'm setting the default colors for the controls. Because again, I want to have the user being able to specify quickly the colors for each module. The other thing I would like you to notice is this one. Let me collapse this one. And this is something I designed on purpose. In the setup event, the same node has been used, but the difference is that one has the setup toggle and the other one hasn't. And the same goes for the solver of the hand. When I'm in setup mode, setup event, setup is toggled on, and in the forward solve, it's not. So going forward, you can think that each complex behavior that you're trying to achieve, in my mind, should have two different ways to perform. One, if it's run in the setup event. One, that it's run in forward solve. Why am I saying so? Well, first, you can see that in order to achieve this, now the graph at high level is very simple. Second, in this, because of the nature of the setup event, you can reuse this node in the third event, which is the backward solve as well. So you can reuse a lot of code, in this case visual code, but still code is. Okay, so there is a lot of reuse there. So let's try to dig a little bit further in what is going on here. And I'm going to start with the simple stuff. In the function section, I have different functions. I divided them in categories, one being solver, and by solver I mean it's a rig logic that outputs basically matrices to move joints. And then utilities, and these can be just a math graph, or it's just simple stuff. Let's start with the very basics. Let's see how I'm dealing with set controls caller. Set controls caller is a simple function that takes a collection, in my case controls, and then a color, and for each item in the collection I am specifying the color. I'm setting the color for it. There is no need to return anything in this function, so I'm not connecting the return. But here it is. I have, for each item in the collection, set control color. This node it comes with Unreal. Set control color. So this function, when it's triggered, it requires a list of controls. It requires color, and it sets all these controls with this color. Now let's have a look at the controls visibility. Very similar. It takes the controls as a list, and for each item is setting the visibility that is specified. So it's either the controls visible or invisible. And this is how I'm doing. You see, right now, being in FK mode, I have no need to have the IK controls visible. So the IK are currently there but invisible. So the user does not select them by mistake, because they won't do anything. Then we have solver pull vector. What is this? This is basically exactly the same graph I discussed in one of my previous videos. And this solver takes three transforms. In this case, these are bones. And by performing some subtraction of vectors and multiplication of vectors, is basically computing where the pull vector should be in order not to have any popping when we switch between kinematics. So it's calculating by basically projecting a vector from here. So imagine that there is a point, a line between this point and this point. So there's a line here. Then I'm calculating the the projection from this point to this invisible line, and then I'm negating it. So if this line it goes back here, here's where the pull vector should be. And the distance between this from here to here, negated, so it's going to be roughly around here, then gets offsetted by pull vector offset. And this is just for visual clarity. If I have a very big arm or a very tall guy and I want the pull vector just to be a little bit far behind or closer to the arm, that's what the pull vector does. What you need to take out of this is that this function takes three bones, a pull vector offset, and outputs a position. And this position represents where the pull vector should be. And I'm using this function in different parts of the system. Okay? So we saw from macro, the big high-level graph, I'm doing basically the same thing. These two nodes are exactly 1, 2, 3, 4. These 4 nodes are basically the same. But in this other one, I'm using basically just I'm just setting the colors that I want as defaults for my solvers. Okay, so basically you can say that these two graphs are identical. The only difference is that one is meant to be set up and the other one is not meant to be set up. Okay, why have I separated the arm from the hand if this is an ARM module? This is because I want to have a solver hand that it's atomic on its own. It takes as an input the whatever bone it's supposed to be driven, is supposed to be the driver of this hand. And this means that I can reuse this to attach a hand anywhere I want. It doesn't have to necessarily be at the end of an arm. It can be attached to a head, and this will still work. That's why it's separated. The idea here is to use atomic function as much as possible so I can reuse them all over the place. Let's keep going with the functions. The last one as a utility function is connect via children, and this is very similar. And this is very similar to the previous function I made in the previous video. But rather than using hierarchy or naming, I'm using the function children, where you can specify something and it will return all the children with the option to have it recursive. So very simple. I'm saying my master parent, it's of type bone. So if I specify, for example, Pinky, this collection here will contain all of these. Why it contains all of these? Because I'm saying include parent, so that bone that I've specified. The children will return only this one. Include parent, so if I use it normally, children will just be this one. If I use include parent, it will be this one. But because I've ticked on recursive, it actually keeps going until the very end. So this children collection is all these 4. And what I'm saying here is I have a branch. I'm saying if I'm in setup mode, the bones are driving the controls. And remember from the previous videos, I'm using this to snap the controls in position without me going to have manually and placing the control closer to the bone and then snap to the current initial position. So if I'm in setup mode, I am saying my bones in this collection are driving these controls in this other children collection. So this one and this one would find, where is Pinky? I have this one represents these 4 controls. And I'm saying for each item of the bones, get the transform of that, give me the index, at the same index, find me the corresponding Pinky. So if I'm inside the loop, and let's say I'm on this bone, because this is index number 1, it will return Pinky number 1. And I'm saying from that bone, set the control offset, not the control, but the control offset, because remember, we are in setup mode here. Set the controls offset of this control, and that's pretty much it. If the condition is false, so we are not in setup mode, do the opposite. So give me the controls, each item, set the transform of sorry, give me the controls, give me the bones, and the corresponding control drives the corresponding bone. So this is, I'm not in setup mode. So this is a quick way. It's very, very similar to what I did in the previous video, literally the video before this one. I think it's number 10. But instead of using hierarchical procedure or specifying a specific string, I'm using the children function. And that's pretty much it. Okay, so we spoke about these. We set the control's color, we set the control's visibility based on a connection. We connect using children, and then we're computing the pole vector. Let's go back to the rig graph and let's see what the hell is going on in the solver IKFK. So the solver IKFK, it's basically using the basic IK, the solver, and it's computing both FK position and IK position. Let's see what happens inside. You can see that even at this level, even if I'm computing something that it's a bit complicated, the graph is very simple to read. Now, I know that these lines are very, very confusing all over the place, but this is always the same thing all over again. It happens to be that I have to connect a lot of things in order to make this work. The very first thing to notice is that in this function, I'm specifying a lot of inputs. I want the start bone, I want the mid bone, end bone, the control for FK, the control for IK, the pole vector offset, again, is to offset the position of the pole vector. I want to know if I'm switching between, if the user wants to be in IK and FK, and I want to know the colors. So let's start and look what's happening. I have a sequence, and this is just for graph organization. The very first thing I'm doing here, really, before even checking anything, I'm setting what kind of controls I want from the FK and what kind of controls I want for IK. And guess what? I'm using the function I just explained before. I'm saying if I'm in FK mode, set the color to FK, set the color to IK, but then I'm also setting the visibility. And the visibility is based on the switch. So if I am in FK mode, if I highlight this, just make the FK controls visible. If I'm in IK mode, take the value of the switch, negate it, and make them visible. So if the switch is on, FK is visible, and because this is on, this node will return off, IK is invisible. And if this is the opposite, switch is off, this will be off, and negate of off is on, so IK will be on. This is the very first thing I do. And if I take this one, I just want to point out that if I go into my settings and I change a current boolean, you can see that I'm changing the color a little bit. It's always the same hue value, but the saturation is different. Okay, so just to identify that I am the left arm in this case, but at least I know that because of the color coding, I know that I'm changing the behavior. Okay, so the next thing I'm doing is I'm checking if I'm in setup mode. Remember, I'm trying to drive everything through the idea of having either setup or non-setup. And here's where the remaining functions are used. So what we're looking now is the solver IKFK. In the solver IKFK, and this is critical, this is where I'm using encapsulations. And I'm sorry that this is going deep and it looks like it's complex, but the winning here is that I can reuse this stuff everywhere, and this rig would adapt for a completely different scenario of bones. So in the solver IKFK, in the setup mode, so here, when this is true, I'm running the solver IK in setup mode and the solver FK in setup mode. Remember, the setup mode, it's simply saying, I want this control to be snapped in the specific position. And once again, I'm using encapsulating. I'm encapsulating function within function to keep the function very simple. So let's see what the solver IK does. So the solver IK, it simply takes start bone, 1, 2, 3, the 3 controls, the fact that is in setup or not, and here I'm introducing an additional thing that we'll see in a minute. But let's keep going. So in the setup mode for IK, so this is true, and simply saying the IK controls offsets are snapped to the bones, so to the specified bones. But the pole vector position is computed procedurally, and the reason it's described in another video. But I want this position of the pole vector to be calculated because I want to be in the most in the best position possible in order to perform the switch between IK and FK. So in the setup mode, I'm just really saying, please bones, controls do snap to the bones. When it's false, I am introducing an additional concept. And the concept is the mode is follow mode. So if I'm not in setup mode, I'm checking if I'm in follow mode. Am I in follow mode? Let's say no. If I'm not in follow mode, I'm simply doing a basic IK. The basic IK is saying it wants the 3 bones that I'm specifying as an input here. So if I highlight this, you can see that this line here is going from one of the 3 bones, and this is the simple basic IK function. And then I'm using the controls to drive the basic IK, and that's pretty much it. You see how simple it is. This is the setup. I'm snapping controls to bones, and this instead I'm moving the bones using the basic IK. Now what happens if follow is true? Follow is the function or the mode I'm using in order to perform the switch when am I in FK. In the previous examples we saw, I was making, when I was in FK or in a completely different chain, in a completely different kind of kinematic solver, I was saying that when the controls are not being used, they need to follow whatever I want them to follow. So in this case, the follow mode is very similar to the setup mode, but the only difference is that rather than being using the control offset, because that gives me the controls in that position but at 0, I'm using the control position itself because I want the switch to move the controls in wall space, so well, not in wall space, but with proper values rather than preserving the constant offset. So these, if you check this graph, if you see, I want my bone to drive my control or my control offset. My control offset, my control. I want my bone, control offset. I want the pole vector to give me the position of the, and set the position of the pole vector control offset, or to give me the position of the pole vector control. So these two things are very simple. So by implementing that directly in the solver, it's easy for me to switch between setup, follow mode, or standard IK solver. This is the actual IK solver. This is what the solver does. So let's go back to, I hope this makes sense. Let's go back to solver IK FK. After that, after the solver IK in setup mode, I'm going into solver FK. Let's have a look at that. Solver FK is very simple and it's very similar. I have the setup mode. If the setup mode is true, please bone drive my control offset. Please bone drive my control offset. Please bone drive my control offset. Where are these controls and names specified? As an input variable of my function. Okay, I always have start bone, mid bone, end bone, control, control, control. Let's have a look at the solver IK. I have start, mid, end, and then the names for the control. Root control, pole vector control, effector control. Then I have setup mode true, we saw it, setup mode false. I'm checking now follow. Is it follow true? Yes. So do the same thing as this. So, but instead of using control offset, use the control itself. It's exactly like the solver IK. So solver bone, solver bone, solver bone, solver bone, solver bone, but rather than using control offsets here, I'm using transform control directly. And then I'm checking setup, it's false, follow, it's false. Let's see. And this is the actual FK solver where I'm simply saying, give me the controls and drive the bones with it. So I get this behavior. I compile it. This behavior, this control here drives the bone, and that's not performing the rotation. Cool. So in the solver IKFK, so you can see that the takeaway here is that, again, I am just focusing on creating very simple behavior, and then the more I go above, the more I travel the graph at a highest level, the more the graph becomes readable and simple to read. So in here, I'm simply saying, in the solver IKFK, I'm specifying the list of stuff that each solver requires. Remember, the solver IK required start, mid, end. The solver FK requires start, mid, end. These are the same bones. But the solver IK required root control, pull vector control, effector control, while the solver FK requires start control, mid control, and end control. So the solver above it, which is this one, has as an input all of them. Has the start, mid, end, the FK, 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 IK, IK, IK. That's why all these lines. It's nothing to be afraid of. So I'm connecting all this stuff in there. So let's have a look then, because this solver, it's very, very similar to what we saw inside. It's the same exact concept. So the first thing I'm doing is basically setting the colors that are specified as an input here. The second thing I'm doing is I'm saying, if I'm in FK mode, make the FK visible and the IK invisible, and vice versa, by using the negate function, the not. After that, after the setup, if I check the setup, if it's true, simply run these two things in setup mode. If it's false, now I'm checking if I'm in switch mode. And this is where I'm using follow, basically. So if switch is true, it means that I want the solver to be in FK. So I'm running the solver in FK, but not in setup. But I'm running also the solver in IK, not in setup, but I'm saying that the solver IK follows whatever is specified as follows, which in this case, the solver IK is following the solver FK. So the controls of IK are hidden, but they're following these bones here. What if I'm not in FK mode? Well, if I'm not in FK mode, this means that it's false, and I'm doing basically the opposite. I'm saying solver IK, not in setup, not in follow mode, but the solver FK is not in setup, but in follow mode. So you see that this is exactly the opposite, literally the opposite. So you could, one of the things you can do really quickly is to implement this is duplicate those nodes, swap them, and say tap, tap, and connect these things together, and you would get this exact same setup. And this is for solver IKFK. So you can see here that we are pretty much done, because the only thing that we need to discuss now is the hand. So we sorted out the order is solver IKFK, and solver IKFK is using IK and FK. Setup mode, follow mode, and standard mode. So you could say that the rig graph contains the solver IKFK, which contains IK and FK. And by structuring the function this way, you can reuse function in different functions without having to rewrite specific things for a specific behavior. You can reuse behaviors that you already wrote, and it will make everything consistent. For a reason, like if you find a bug somewhere and it's a big bug, it's easy to see it, and then you can fix it in just the function. and it will be propagated across the whole rig. If I have to do a leg instead of an arm, it would be pretty much the same. It would be just a matter of me saying, copy this solver IK into my leg module, and that would be it. And I'm hoping, as I mentioned already, that Unreal will eventually provide a way to expose this function in a more generic thing. So this function in a more generic asset than real asset, so you can read this function from everywhere in any control rig. So let's have a look at the hand, and the hand is really, really simple because it's, even if it doesn't look like, I realize that, but let's explain it. So the function takes the hand bone and the hand space. So it just want to know what the hand needs to follow, and the hand always needs and only needs to follow whatever is at the end of this bone. Okay, so the hand in setup mode, it says connect via children, and this is the function we explained before. And I'm saying that the master parent is the bone and the slave parent is the control. So it's going through all the bones. So in here, what's happening here is that I'm taking the middle, for example, all of these, and I'm saying respectively drive all the control offset of these. And remember, I am driving the control offset because I'm in setup mode. So in here, you can see that basically I am saying I want all these controls to be snapped to the corresponding bones. 1, thumb, index, middle, ring, pinky in setup mode. And I'm also saying I want this space to follow always whatever is at the end of the chain. It doesn't matter if it's an IK or FK. I want always to follow. I want always the hand, let's say. Let's pick I want this hand always to follow whatever is at the end, no matter if it's an IK or an FK. So this is what you are specifying as a hand bone. So we are in setup mode. We are not in setup mode anymore. So it's false. So we are solving, and the solving is saying exactly the same, follow the bone, but also connect via children. Same 5 nodes, but not in setup mode, right? So in this instance is the controls that are driving the bones, okay? So I realize, and I'm very aware that this is, as I mentioned, I wanted to build things slowly, and this is the first case where I'm taking everything that we went through so far and make it, a little bit more complex behavior. Additional things that you can do is, for example, in my variable, you can say set controls color. In my variables, you can say that when it's in FK, it's red, and you can see that I'm specifying the same color also for the fingers. The fingers do not switch kinematics at all, but I just want to have a nice clean interface for the user, so they always know if they are in FK and IK. So it's just a little bit nicer to watch. And let's pick this one. Okay, switch. Let's switch. You see it switch without changing the shape of the thing, and the IK color, instead of being this one, could be whatever you want. So now when you and this is the set color function. So now that you are here, you can change between those two colors, and this is what I mean by customization. You can have this variable at a very high level, and you can tell the user, okay, I just want to change the colors for everything. Or you can build a function that you can say if this is a left arm, always shade them of a blue with a different saturation maybe. If they are right, always shade them red. You can do stuff like that. There is additional stuff that I have not implemented because it's just trivial and I didn't want to complicate the graph even further. But basically, when you are in IK mode, it's very, very simple. I'm not using the stretch or the stretch ratio or the first bone length These are simply things that you can drive by exposing this attribute as a new variable. So like if I call this stretch, you could connect these things here, and so this is just an exercise of adding this as an input in the function and connecting them directly here. And then in the graph above, you can expose those as controls to the user. So in the graph above, you would have, let me get rid of it. Sorry, not get rid of it. I mean, so let's go back to IK. Now you can see that in the IK, where I'm using the IK, I have stretch now, and this is something you can expose as an attribute here, or as a control. That's pretty much it. So the user can say, okay, the control is stretching, it's not stretching. I didn't want to do that simply because, well, it's so simple. It's just a matter of connecting things. But also I didn't want to overcomplicate the graph, because I do realize that this is already, I mean, it's daunting, but honestly, it's way simpler doing this way, and it pays off in the long run, because this rig will adapt to any configuration, and you will be able to use this thing all over the places. Like the solver IK FK, every time you have two bones that needs to either be an FK or IK, this is what you would reuse, and you would change just the input in the rig graph. You just change the names here, and everything will snap in the right place, and the controls in the right place, and they will switch already properly. I hope this makes sense. Let me get rid of the stretch thing and compile. So yeah, well, we knew this was coming, but I'm hoping that this explanation makes sense of why I made certain choices. Thank you so much for listening. Bye bye.